I'm very glad to say that my colleague, Joe Wallace, is going to introduce our speaker today, so I'll hand over directly to Joe, who will introduce.
Thanks, Ed. I'm not mic'd up, so I hope you can hear me. If you can't, come a little closer. I've scripted this, so pay attention. Dr. Ruth Siddall is a geoarchaeologist who applies analytical techniques to further understanding of cultural material, primarily pigments. Her research ranges from the analysis of medieval mortars in the Cosmati pavements at Westminster Abbey, paints and plasters of Romano-British villas. She has worked in the temples of Venus in Pompeii and the agricultural terraces of Antikythera in Greece. Somebody taught me to say that day. I've had the fortune to work with Ruth alongside Dr. Spike Butler from the Carr Institute on the Corslin on a research project turning landscape into colour that examines 5 earth materials taken out of the British landscape. Ruth is co-author of the Pigment Compendium. It comes in 2 vast volumes. One is a comprehensive dictionary of historic pigments. It begins with al, which is a common name for a particular type of madder used in 17th century India, and ends with Schweikart yellow, which is a synonym for chrome yellow that was manufactured in Saxony. The other equally vast tome contains optical microscopic images of pigments, which, apart from their scientific excellence, are simply exceedingly beautiful. And for the last year, this compendium has been my Bible in my studio while I've been attempting to make a pigment timeline of historic and contemporary colours. Ruth is also developing a pigment reference collection, with currently over 600 pigments, and she generously makes this available, which is a valuable resource available to staff and students at UCL. And from this, she has donated numerous samples to the Slade Material Research Project Pigment Library. Currently, along with Gary Woodley at Slade, we are working together on a pigment timeline project. This will be a pigment colour timeline of UCL. Its aim is to establish a database of departments who use pigment and colour in their research. This knowledge will be translated onto maps and plans of the university as walkways of colour. Do you like that? Okay. Over the years, Ruth, I've been impressed by your extraordinary depth of knowledge you hold for your subject, and equally for your sheer love of it. And I'm delighted you are here tonight to share with us that passion and expertise with the Slade. So would you please give a warm welcome to the wonderful Dr. Ruth Siddall.
Thank you, Jo. Thank you. Can you hear me? Great. Thank you very much, Jo. That was a very, very nice introduction. I should also say as well that Jo has contributed a huge number of samples to my pigment reference collection. It hasn't just been a one-way thing, and I'm very grateful. As Jo introduced me, I'm a geoarchaeologist, and actually I started off my life as a geologist. And if you're coming to this talk expecting to be blinded by science, I'm afraid I'm going to have to massively disappoint you. So I'm not going to show you any graphs or numbers or equations unless you really ask for it, although it's quite useful being in the chemistry auditorium and having the periodic table of the elements on the wall, because these letters and numbers tell us a lot about the materials that we're going to be looking at. And what I'm going to talk about tonight is just, as the title says, a series of pigment stories. I became interested in pigments, first of all, because I started working in Roman archaeology and looking at building materials initially, but painted building materials are obviously a lot more interesting than unpainted building materials. And so my first foray into pigments was actually at ancient Corinth. This is actually Herculaneum in Italy, in the Bay of Naples area. And it was an interest in these materials and how they were used in the plasters, how the technologies of fresco and secco painting that the Romans were using then grew into an interest of where they were getting their materials from. So sometimes I get to look at buildings that look like this. Most of the times my samples end up looking like this, bits of cruddy Roman fresco that have been dug out of a pit somewhere in the South Pennines, or actually in Lincolnshire in this case. So yeah, the Romans were painting in Lincolnshire. So this interest grew into work with my colleagues Tracy Chaplin, Valentine Walsh and Nicholas Eastor, who are painting conservators, and Tracy's a chemist. And we put this together to form the Pigment Compendium, and ever since I've just been an avaricious collector of pigments, and this is just a selection of material that I raided from Joe quite recently. So I'm interested obviously in the colour, and I'm interested in why people chose those colours and why we use these colours in art, but I don't look at them necessarily at a macro scale like this. I put the material onto a glass microscope slide, and these are some slides. They're about 2.5 inches long by about 1 inch wide, so they're not very big, and you can see on some of them the dispersions of colour. We call these grey mount dispersions. So a tiny amount of pigment melted into a resin. Well, the pigment doesn't melt, the resin's melted, and you put a little glass cover slip on it, and you can look at it underneath the microscope. And, you know, if you were an archaeologist, you would be now probably asking me, well, this is a really destructive way of analysing materials using paintings, because you have to physically take the pigment off the painting. Well, you do, but you can get away with tiny, tiny amounts. Most of the time, these are materials I had lots of. Most of the time, you can't even see the sample on the microscope slide. So we can do a very tiny amount of pigment can give us a huge amount of information. So this is me using my microscope. It's a top-end microscope. I wouldn't say it was a Porsche of a microscope, but it's certainly a Mercedes of a microscope. This is not what you'd find in the average teaching lab, but it is a microscope that uses visible light, by which I mean a light bulb, so no fancy electron beams or anything like the kind of clobber they have in chemistry here, and my eyes. And all the magnification is done purely by lenses. And what makes this a Mercedes of a microscope is that it will magnify up to the best possible, the optimum possible magnification that you can do with the human eye and lenses, which is 1,000 times magnification. So we can see a lot of detail of small particles. It's also a special kind of microscope that geologists use that uses polarizing filters as well. And again, if you went down your average microscope shop, bought a microscope, it wouldn't have these polarizing filters. You'd have to ask those as, you know, extras. But what polarizing filters do is allow us to see the material under the microscope in 2 forms of light. So we've got a bright field version, which is effectively looking at the pigment. This is lead chloride oxide, a pigment called Turner's yellow, in white light, and that's the colour it is. It's a yellow pigment. And then we can look at it in this dark field view, which shows polarization colours. And as geologists, we're taught to recognise minerals and identify minerals by their physical and optical properties when we see them under these 2 different light sources. And I got particularly into this as an undergraduate geology student because they're just so beautiful and trippy to look at. So you get these amazing plays of colours in polarised light, and you get these very anomalous colours. So you can see these beautiful shades of violet in the dark field image here, which are nothing to do with the polarisation effects. It's a combination of those polarisation effects cancelling out the yellow colour of the pigment itself. But I won't go into science, I promised you that. We can use other techniques. This, for example, is smalt, cobalt-doped glass as a pigment. Brand new, fresh smalt. Ancient smalt tends to fade. But we can put a special green filter into the microscope as well, which was actually developed in the gem industry for identifying emeralds, mainly. And it's called a Chelsea filter. And certain blue and green pigments are red when you put the Chelsea filter in. And smalt is one of them, cobalt blue is one of them, ultramarine is one of them. But things like Prussian blue and indigo and azurite and blue verditer, blue bise, they stay blue under the microscope. So, you know, other little techniques can help us identify things. And then we can actually play with the speed of light. This is an image of strontium chromate, chrome yellow. And these are the crystals of strontium chromate in white light. But we can change the speed of light and actually slow it down or speed it up for some of these particles by putting a special filter which changes the wavelength in, and we can get these amazing images like this. And so the light is being sped up in the crystals that are oriented like that, and slowed down in the crystals oriented in the opposite direction. So using all these different techniques and learning them, and to be honest, learning them is just pattern recognition. You can diagnose, you can characterize what the chemical compound is that you're seeing. So the chemistry, or in fact these properties seen under polarizing light with these various accessories, are a proxy for the chemistry of the material you see in them. So that's why we use this technique, and it was developed, of course, not so much to aid fine artists, but to analyse pigments in archaeological context, which is what I do, but also to detect fakes and aid restoration and conservation of paintings as well. And that is, of course, the main use of it today. And people like me who publish these volumes explaining exactly how these ancient pigments were made and how they're analysed is probably been a huge boon to fakers. And I reckon most of my books were probably bought by painting fakers, but there you go. So, you know, it is giving away secrets, I guess, but it's a very, very powerful tool for characterising pigments. Not only that, because you're actually physically looking at it with your own human eyes, you're seeing the real colour. And you're also seeing other choices that artists made. Now, many of the pictures I'm going to show you tonight are pretty much pure pigments, as you would buy them from the colourman, the colour dealer. But of course, artists would mix them with other materials, with other pigments to make different colours, with fillers, with secatives, drying agents, with all kinds of things. And of course, then you have to mix them with a medium to apply it in whichever way you need. Now, the good thing about media is they don't tend to show up at all in these techniques. So, unfortunately, this is not good for identifying media, and I'm afraid we pretty much ignore them. But here's an example of a mixture of a pigment. This is carmine, cochineal, effectively, from insects, which is a dye, and is effectively a liquid in its natural state, but it's been used here to dye cornstarch to make a pigment. Now, if we use any other chemical technique, you wouldn't pick up the really light elements. If you look at the periodic table here, you may think, oh, what's all that about? But anything that at the top is what we would call a light element, and it literally is light in weight compared to the stuff. They get heavier as you move down. And the light stuff, if you look at 5, 6, 7, 8, 9, that stands for boron, carbon, nitrogen, oxygen, fluorine. These are too light to be detected by most chemical analytical machinery. And actually, that's what most organic compounds are made of, and hydrogen and helium, which are 1 and 2, the H and the HE at the top. You can't pick those up using most chemical analytical material, but we can see them. We can see them. So if you analyse this using fancy chemistry stuff, it would just tell you it had carmine in it. And it wouldn't tell you it was bonded to starch, but we can see these beautiful starch crystals here. So pigments can be made of 3 main things. They can be geological materials, and this is a fairly low-grade ultramarine, but natural ultramarine. But I chose the low-grade one to show you here because you can see all the impurities that are in it. It's not the pure blue ultramarine crystals alone. So there's black stuff in there, which is iron pyrites, which doesn't transmit light, so it just appears black. It's a metallic-looking crystal. And then we've got other things like calcite and all sorts of junk in there, to be honest, as well. But a geological origin from this, and when we look at it on the microscope, that is very clear. We can then have pigments that are made from organic compounds, and I just mentioned carmine from cochineal. This is Tyrian purple, which is a kind of mucus-like thing that is excreted by certain shellfish, and then it's oxidized, and you get these amazing purple compounds, and I think you get a feel of its kind of mucilaginous nature from this slide. And then you get pigments that are chemical precipitatives, they're completely synthetic. So they've been made in a laboratory or an alchemist's workshop, either by accident or design. And this is cobalt green, cobalt zinc oxide, which is one of my favourite ones. It's very obvious when you see it down the microscope. So it's very reassuring when people ask you to analyse pigments and you know what they are. It's always good. So I'm going to talk, for the rest of the talk, I'm going to take a bit of a tour around the colour wheel, but mainly in the primary colours. This is a particularly nice colour wheel by Clay, who, like many artists, was particularly interested in colours and the pigments he was using. And as I'm sure you know, many artists became very obsessive about certain shades and certain colours, you know, to extremes. Yves Klein is obviously an example. But, you know, you see this historically as well, even back to the Roman period. In fact, if you go to the British Museum in the Roman galleries, there are some pigment pots from, I can't remember which site, but they are from, I think, somewhere in the UK. And they are the most horrendous day-glow colours I've ever seen in my life. And you just think, what was that room going to look like? It must have been awful using those colours. But, you know, there was a clear choice to use these day-glow colours. I've no idea what they are. I need to get onto the BM about that. But yes, you know, colour was really, really important. And actually, pure colour was important. You know, we may choose to make a green by mixing blue and yellow. But actually, to a lot of artists, and especially in the Renaissance, this was looked upon as not a good thing to do. And artists like Cennino Cennini wrote manuals and treatises on the use of colour, you know, and they would often say, you know, if you want to change the shade, if you want to make a dark yellow, for example, don't mix it with black. Just choose a yellow that is darker in hue than the one you already have. You know, so people would go to huge lengths to get hold of these colours. Of course, there was some mixing, and again, that's quite a useful thing. You can actually see it under the microscope. So I'm going to start off with red, and this is probably one of my favourite pigments. This is cinnabar or vermilion. I'm using these two words to differentiate the natural geological product, which is cinnabar, which forms these beautiful red crystals, as you can see here. This is a macro image. These crystals are about, well, that whole cluster is about 1 centimetre across, just under 1 centimetre across in diameter. And it's mercury sulfide. And you might kind of get a theme going here with me with these, because I do like poisonous pigments, actually. And this is certainly up there in the poisonous pigments. It's found naturally associated with gold deposits and also around certain volcanic vents and fumaroles. And, you know, these are not great places to work, you know, to go and send somebody to scrape it off, you know, with 150-degree gas coming out right next to them and bubbling mud and all sorts of stuff. But that's how they would have found it. Or, as I say, it would have been a byproduct of gold mining. And actually, liquid mercury, so mercury is number 80 on the periodic table, Hg, and it is a metal in its native form, but it's the only metal that's a liquid at room temperature and pressure. So I'm sure you've seen mercury in thermometers, and it is quite an amazing material. And actually, one of the main pigment sources for native cinnabar were mines in southern Spain in a place called Almaden. And the cinnabar ore there literally bleeds quicksilver. And so this liquid metal is just kind of bleeding out of the rock. It's the most weird thing to see. I have got some in my office, but for health and safety requirements, it's not the sort of thing you can pass around a lecture theatre. but it's a very earthy red crystal. These are from China, and these crystals formed around volcanic vents and fumaroles. And cinnabar was quarried from these environments and used in Chinese scroll painting, and indeed exported to Japan as well. So Spain and China were major sources. And then probably in the Renaissance, but possibly in the Roman period, they learned how to make cinnabar synthetically. And you do this by getting hold of some quicksilver, liquid mercury, and heating it up with sulfur. And the minute you start heating mercury over about 30 degrees C, you convert it into a gas. And of course, if you're standing there watching it, you're breathing it in, and then it will collect on your lungs, and it's a really dense thing, and it will kill you if you ingest enough of it. But if you burn it with sulfur, it will produce vermilion, and this is vermilion. Actually, vermilion and natural cinnabar look almost identical if you see them under the microscope. They're very difficult to distinguish. And as you can see, it's red. It's slightly orangey red, which is a little bit unexpected, I suppose, if you know the colour of it. But slightly more orangey red than cherry red. But when you look at it in the dark field, it's this amazing, it's almost impossible to photograph. It's just so bright. And it stands out a mile when you see it under the microscope. Another reason why I like this pigment, very easy to identify. And it's an amazing scarlet red colour. I'm sure you know it. This is an image. I did some work with Gemma Angel. I don't know if any of you know Gemma. She recently completed her PhD about a year ago looking at tattoos, Victorian tattoos. Think about it. Those people have been dead over 100 years, but we still have their tattoos. And one of the things that Gemma found in most of these people were sailors, and I don't even want to think about how their tattoos got cut off their corpses, but they did. And most of these people were sailors, obviously, and there were papers written in the Lancet about 150 years ago by doctors working in places like Marseille who noted that the sailors with red tattoos didn't have syphilis lesions on their arms. And those that had black tattoos did. And so one of the questions that Gemma was asking was the red poisonous? Was it mercury sulfide? And yeah, this is a flake of human skin with tattoo ink in it. And it's this bright red cinnabar, instantly recognizable. Don't ask me how I got a hold of that. But this is also one of the earliest pigments that have been used. Another one of my PhD students, Dugu Kamakoglu, in archaeology, works at Çatalhöyük, which is, I suppose, famously in terms of an archaeological site, it's often described as the first city. And it's been going since about 12,000 BC. And the people that lived in Çatal were not like us. We don't really understand why they lived in the way they did. They had nice little houses that we can kind of understand with a hearth and little shelves to put your stuff on, and then there'd be a little kind of shrine area and places where beds are, and then you'd have Granny buried under the floor, in the middle of the floor, and then on your little shelf you'd have a nice dog turd, and, you know, don't really know what they were going on about. And they all were living cheek by jowl. And they also painted their walls probably 5 or 6 times a year. And this image here, which Dugu took for me, shows these. At first you think they're handprints, but they're not. They're actually painted hands. You can see the brushstrokes. They're not prints of hands. They're paintings of hands. And they are hand-sized, though, but they are paintings. And they're painted with iron oxides mixed with vermilion, which gives them this really kind of luminous red. And we're under a kind of protective, rather gloomy cover here, but even in this rather dark and gloomy environment, you can see this vermilion red shining out. And they also painted their walls And Dougal came into pigment analysis because she was one of the conservators at Chapelhoek, and it was her job to kind of consolidate the wall paintings. But each wall painting is painted on a layer of plaster less than 1 millimetre thick, and there may be 50 on each wall. And so, you know, it's like painting the Forth Bridge, trying to restore and conserve these things. So this is just a picture of one of the rooms. Another thing that they used to have just randomly was a big bison skull in the sitting room, or sometimes little vulture skulls stuck on the walls. They're kind of cute, actually. But you can see, again, red paint on the wall and also on the ox head, the bucephalon that they have here as well. And we found evidence as well for painting materials and techniques. These are mussel shells, freshwater mussels, which were used as palettes with traces of vermilion pigment in there. And we knew that they were cutting this vermilion with iron oxide because we can look at it under the microscope. And this is the plaster layer under the microscope with the paint on the top, and we're looking at a field of view about 1 millimetre across there. But when we really zoom in to the tiny particles, this is at 1,000 times magnification, you can see again these bright red spots of the vermilion, or cinnabar in this case. It would have been the natural mineral shining through, and otherwise quite dull iron oxides, red ochre. And this is a good image to show you that difference in terms of the contrast and luminosity of these two pigments. After ultramarine, vermilion was the second most valuable painting in the Renaissance period. And, you know, as you all know, Madonnas would be painted in blue because it was all about the money. And if you didn't want the blue or couldn't afford it, then you would go for the next best offer, which is the red, as in this Jura. But this painting also shows one of the problems with ultramarine. You can see in parts of her robe, it's getting a bit black. It's kind of getting patchy and mottled. And this pigment reacts with light, and actually we don't know why yet. We still don't know why this happens, but sometimes it blackens. And this has been blamed on sea air, it's been blamed on light. Various compounds have been accounted for, but actually we haven't been able to nail it. And I know that because I've even been down with vermilion to the synchrotron at Oxford, the ISIS, and like zapped it with high-powered X-rays, and we still can't tell what the material is. So it's a mystery. It's a real mystery what is making vermilion blacken. But even back in the Roman period, Vitruvius wrote, you know, don't use this pigment if you're going to have it somewhere where it'll be hit by the rays of the sun or the moon, because it'll go black and you'll have wasted all your money. And apparently, I don't know, but the stores of all the great art galleries in the world are full of cardinals wearing dirty black robes because of this. And you can see this starting to happen. It's clear that there's a different colour that Jura was choosing here for the robe and the underdress, but the underdress is certainly in a much higher quality material. Okay, I'm going to move on to yellows now, and I had to choose this yellow. This is my favourite yellow, Indian yellow, and this is a lump of raw Indian yellow pigment from the Windsor and Newton archive, and Jo has a lump of this as well in her studio. And this is my only bit of text in this talk, but I had to put it there. It's made, or was believed to be made, it was made from the urine of cows that were fed exclusively on mango leaves in India. And it was manufactured in the 15th and 19th century. Now, Victoria Finley, who is a popular science writer, did some work on pigments and colour about 5 or 10 years ago, and she went to India to try and research this, and nobody would talk to her about it. And she came away concluding that this maybe was a myth. It was banned by the British on the grounds of animal cruelty. Imagine that in the Victorian period. So it must have been bad. But it gives you this amazing yellow, and we can see Krishna, who always looks like he's on roller skates to me in that picture. It was blue, and the blue is indigo, and his pantaloons are in Indian yellow. And so Urine comes into pigment manufacture quite a lot. I won't dwell on it, but as you can see, this article written in the 1880s says the urine is collected in small earthen pots, cooled, and then heated up so it evaporated down, sieved, and you get this yellow sediment which you could form into a ball, and that's what I've shown you here. So we have, this is from the Winslow Newton archives. It's over 100 years old. We have evidence that this is happening. And when you look at it under the microscope, kind of looks like you'd expect it to do. Yellow, slightly orangey yellow. When you cross the polars, it looks like nothing else that I've ever seen. And you get these kind of three characteristic components. And you don't get this in things like tartrazine, which is, if you went and bought Indian yellow hue today, it's an organic pigment called tartrazine, which they also put in orange juice to make it look more orange, and kids go crazy. But this is the real thing, and it has these kind of mats of yellow fibres. But if you look carefully, you'll see little blue sticks in there as well, and little white clover leaves. And these three components are what you look for, and there's nothing else that do that. And chemically, it is compounds that are formed in rather weird urines. So it was made, unfortunately, from the urines of emaciated, poor, starved cows. The nastiest mineral yellows, actually I've chosen kind of red and yellow here, orange, are the arsenic sulfides, orpiment and realgar. Orpiment is the yellow one, and it's often found with realgar, which is a kind of orangey red to ruby red coloured mineral. And they almost have, the two minerals, orpiment and realgar, have very similar chemistry. They're both arsenic sulfides. So they contain arsenic, number 33, and sulfur, which I can never remember where it is, number 16. And arsenic is shockingly poisonous. And the problem with, I'm going to give you some chemistry, just because I'm in the chemistry auditorium, right? So pay attention. So that's realgar. It's got 2 arsenics and 2 sulfurs in it, and it can react with oxygen, O2, not just a phone company. And it does that because we've got oxygen in the air. I'm not going to balance this equation, but you end up with arsenic oxide and sulfur dioxide, which is a gas. So that goes off into the atmosphere. It's not bad for you, but it's not the best thing to be breathing in, sulfur dioxide. It smells like rotten eggs. It's horrible. It comes out of volcanoes. It's not good. But this, arsenic oxide, is white in colour. And this was the poison of choice if you were a Victorian wife and you wanted to get rid of your husband. And that's because this oxygen will bond with the hemoglobin in your blood, depositing pure arsenic in your body, which will kill you horribly, quite rapidly. So this is really, really nasty stuff. And I went to a talk at the Tate last week, and the conservator there said, but don't worry, if these are combined in a medium, in a painting, they're absolutely safe. That's not true. That's not true. So you need to be careful. So these things, again, like cinnabar, mercury sulfide, they can be deposited either with gold mineralization, so you find them with gold veins, or around volcanic fumaroles. And here's an example of a volcanic fumarole in the Campi Flegrei in Pozzuoli, in the Bay of Naples. You can see all the steam coming out of it, and you can see around the orifice of the fumarole, the rocks have been stained orange with realgar and yellow with orpiment. And this is nasty stuff. And there were blokes sitting around there with in deck chairs, and they were selling off these coloured stones to kids, take home as a souvenir. I got a few off them as well, but I keep them in a box that I never open. And the problem with this, should have said, this reaction happens at this temperature, right? You don't really have to heat it up to produce one of the worst poisons known to man. It will just happen ambiently. If you do heat it up to about 200 degrees C, instead of producing arsenic 2 oxide, you produce arsenic 4 oxide, which means there's even more arsenic in, and it gets even worse. So there's no kind of good way around this. And, many people like Dumayen and Chenini, who were writing treatises for artists, they said, it's a beautiful, beautiful shade of yellow, but don't use it. But it was used. I often think about it. You don't see it that much in kind of easel painting, art historical works, but you do see it in Egyptian painting a lot. And this is a foot case of a mummy. So if you can imagine an Egyptian mummy, he was all covered in bandages and he had a mask on. His feet were in this kind of box, and we're looking at the bottom of the box, and he had his enemies bound under his feet. So he knew where they were in the afterlife. But the yellow on here is orpiment, and it's not that bright yellow because it is fading. This is in the Fitzwilliam Museum in Cambridge, and they also have a Book of the Dead scroll there as well. And you can see the orange hieroglyphs at the bottom of this image are Realgar. And this scroll was scrolled up, so it wasn't really exposed to the atmosphere, so there hasn't been too much alteration. The Realgar's in good condition, but the yellow, you can see fragments of what actually would have been a golden calf. It's going white, and the white is white arsenic oxide. It's these incredibly poisonous materials. It looks yellow under the microscope, and you get, again, quite impressive textures and colours in the dark field. Realgar's lovely as well. Looks more yellow than orange under the microscope, or red. And it doesn't transmit light in the dark field. So you get these black centres to the crystals, but they are very reflective, which is what you're seeing, this glow in this image. And Realgar reacts in presence of light. And actually, this is my jar from my office. And you can see it's kind of yellowy orange. The colour's pretty true on this image. And when I opened the jar and looked in it, that's what colour it is inside. So this is changing quite dramatically. So I went to see the Sigmar Polk exhibition at the Tate last week, and this is a painting in it. And it probably is amazing, the biggest painting ever made using arsenic and Realgar. As you can see, it's 2.6 by 2 meters. It's a big, hefty painting called A Limp of Gold. And Polk intentionally chose poisonous pigments to paint this with. So he's using arsenic green for the green background, and these shades of yellow and orange and gold, which are Realgar and orpiment. And this is the image that the Tate are using in their publicity. But go and see this exhibition, because that lump of gold now is just matte yellow. All that tonality is gone. But Polk did ask conservators to leave his work alone, that he knew this was going to happen, not to touch them. But I think it's unfortunate they don't have a picture of what it looks like now, because you lose all this tonality. I kind of like that, because even though it's like kind of a 1.5 meter chunk of painting about orpiment and Realgar, it really reminds me of these shapes that you see down the microscope. There's kind of a fractal thing going there. Very quickly, I'm going to finish off now on a blue mineral. And again, I thought I could have chosen ultramarine, but everybody goes on about ultramarine. So I've chosen Vivianite, which is blue ochre. This is, again, a naturally occurring blue soil. In this case, this is from Hampshire. You can see these kind of dark blue-grey crystals on this chunk of limestone, just any old limestone. It's also known a lot in Russia, and this amazing image is a picture of mammoth ivory. Vivianite is iron phosphate hydrate, and we've got iron in the groundwaters that are reacting with the phosphate in the mammoth ivory bones and turning them this amazing blue colour. And it was used, it's very much used as an ethnographic pigment. The Maori used it. This is a shell palette from Te Papa Museum in Auckland with some Vivianite in it. Pukepoto, the Maori called it. And this is what Vivionite looks like under the microscope, and this sample was collected for us by ethnoarchaeologists working in Papua New Guinea, where it was used as a body paint. My favourite use of Vivionite was on these masks and other artefacts made by Pacific Northwest. They actually call themselves Eskimos up there, so it's actually politically correct to call people from Native Americans from Alaska Eskimos. And they use Vivionite along with red ochre and yellow ochre. And most ethnographic art that you come across is using red, yellow, and black and white, because these are the earth colours you can standardly get hold of. But on Nelson Island, off Alaska, you can also get Vivionite. And so they also use this blue. And I visited Anchorage a few years ago and went to an exhibition of UPIC art and artefacts. And they had various recordings there of local people talking about how they process materials. And the reason I've included Vivionite as my last pigment here was it was the best story, because this very elderly man said he used to go with his grandfather in a kayak to Nelson Island, where the Vivionite came from. And this was surrounded by very tall cliffs. And they would go on a calm day and try and get as close to the cliffs as possible. And the son, the grandson, would be in a smaller kayak, and he'd be ready to go, and his grandfather would get a rifle out and shoot it off the cliff, and it would fall, and he had to paddle like hell and catch it and put it in his kayak. And yeah, that was, I've never heard anybody going to those kind of lengths, but yeah, they used to shoot it off the cliff because it was high up on these deep cliffs. But it forms in kind of peat bogs, to be honest. And you can get it in peat bogs in the UK. I've never found it in Roman painting, but some people reckon they have. It was used in Russian icon painting, and that's where the mammoth ivory comes from as well, is from bogs in Russia. But some evidence it was used in Russian icon painting. But the main, I suppose, verifiable use of Vivionite as a pigment art historically is in medieval wall paintings in southwest France and the Pyrenees area. But I'm sure they didn't shoot it off the cliff. Anyway, I shall end there. Thank you very much for listening. This is Joe's pigment collection, just to finish off with.
Thank you so much, Ruth. Ruth is very generous and said she'll have to take some questions from the floor.
Oh, my tea.
Room for about 2 or 3. Unfortunately, I have one.
Okay.
But I think let's start with you guys first. Do you have any questions for Ruth after that fantastic lecture?
Thank you.
Explain in a bit more detail, but maybe in slightly more layman's terms, what's happening with that dark field in the microscope?
Yeah, it's well, I can't explain it in layman's terms, but I'll do my best. Actually, if you think about it, if you've got sunglasses, polarizing sunglasses, yeah? Now, you're seeing darker. Now, what is actually, if you could zoom in on that lens with a microscope, you would see actually there's millions and millions of very, very finely spaced lines on it, vertical lines. And you can see through it because effectively you're seeing light that has been forced to vibrate just through those lines. Okay, so instead of light normally coming from any light source in here, it's going out in 360 degrees every direction. But when you're looking through those sunglasses, the light coming in through the sunglasses is being forced to just vibrate in one plane. Now, if you broke those sunglasses in half and you had one like that and turned one through 90 degrees, put them together, you would block out all the light and it would go black. You can try this with a pair of cheap sunglasses. Now, if you insert a crystal in between that, crystals have complex enough structures that when light flows into them, it's twisted. So crystals have the effect of twisting the light back, but not properly, so you don't get the light of the same wavelength, i.e. colour, that you should see. And that is as simple as I can make it. But then the thickness of the crystal, the chemistry of the crystal, and other factors influence the colour of the light. And actually, that colour that you're seeing in the dark field is formed exactly in the same way as you see colours when you see oil on water. It's called Birefringence of Light. And it's actually the light is kind of vibrating and reflecting in a very, very thin layer, which is your tiny slice of crystal. And I should say these crystals I'm showing you on the microscope are less than 40 microns in diameter, and 1 micron is a millionth of a metre. So these are tiny, 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 tiny specks. You wouldn't see them if it was on your hand. Does that make sense?
Yeah. Can I ask my question before, which I'll try and keep short? It's actually not to do with, it's about arsenic.
Right.
And I've been working on a project with archaeology to do with bronze, and we were working on a project that involved arsenic.
Mm-hmm.
Yes, I think a flux, but you would know better. I'm not
Possibly. I don't like the sound of that, though.
But strangely enough, I was not allowed to use it in the project.
I'm really glad to hear that, Ed, actually. I'm very relieved, and that's why you're looking so hale and hearty tonight.
I'm not sure about that. But, so that a lot of Japanese bronzes, a lot of very early bronzes were alloys of arsenic,
Yeah.
which I understand is a
Well,
metal.
yeah, arsenic is in certain coppers, and
Okay.
so it's kind of there as a trace. Actually, it's actually more common in lead compounds and iron, actually. So yeah, it can be there as kind of an alloy, a natural alloy in the metals. Yeah.
Okay.
So I mean, I come from Salford, and in 1900 or thereabouts there was a major arsenic poisoning case because people were drinking beer, and the beer had been made, and you use sulfuric acid somewhere in the beer making process, and the sulfuric acid had been made from iron sulfide from Cornwall, which was particularly rich in arsenic, and the arsenic got into the beer and killed 2,000 people.
Oh dear.
And then they found out, and they emptied it all down the sewers, killed all the rats, no cholera.
Okay. Well,
Right side.
I'll worry about some of this. So some more questions. Richard.
Are there any pigments we've lost?
Yeah, a lot of them have been recreated because artists were always, thankfully, quite nerdy about pigments, so they did write down how they made them. And I think because many of them were made by chance first time round, it's like, right, we've got to write this down, so we'll do it properly next time. So we have recreated them, but I'm just trying to think of things that have been completely lost. I think most things have been created. Things have been lost for a long time, like Egyptian blue, which was the main blue used by the Egyptians and the Romans. And then it was only resynthesized about 50 or so years ago. But it's quite easy to make, actually. But yeah, so that was lost for a couple of millennia. Turner's yellow. I know, that was that lovely one I showed you. It's my first light field and dark field image. I can't get hold of any of that either, and we've lost our original sample of it. Well, it's not. It's azo yellow. Yeah, I know. I've had a look at that. And yeah, so I'm trying to get Andrea Sella in chemistry here to make me some. But the recipe sounds really scary. Yeah, you've got to kind of like burn it with nitric acid and stuff. Yeah, Mr. Turner. Yeah.
But I've only seen pigments, and I've got this kind of
Yeah.
thing about it.
But yeah, things have been lost and then remade, but what we haven't done is made them in those traditional low-tech ways, and that really alters the behaviour of a pigment in terms of its particle size. So, you know, lead white made in the 15th, 16th centuries, we can't make lead white that looks like that anymore, you know, proper flake white.